A machine learning model has a bias factor and a variance. What are the characteristics of a high bias model and a high variance model? Neural networks are especially prone to this problem of overfitting the training data. This basically means that you tweak your model parameters to an excessive degree such that your model performs really well on your training data set. Maybe the accuracy for predictions on the training data is very high, but it performs very poorly on test or validation data. Out in the real world, your model isn't that great at all. Let's understand overfitting and the bias variance trade off using the very simplest of our machine learning models, that is regression. The whole point of regression is basically that you have a number of points or dots in space, and your challenge is to find the best curve through all of these points. Now, there are a variety of curves that you could fit through these points. Let's consider whether this curve is a good fit, and it seems like it is. A curve has a good fit if the distances of the various points from the curve are small, if they are minimized. This is the whole mean square error that we've discussed earlier. This curve here we say is a pretty good curve. It's a good representation of our underlying data set. We could also make the curve overly complex. We could have it pass through every point, every single point in our training data. Now, it's pretty clear that if you were to use this curve for regression and you choose points from your original training data set, this curve will totally nail their values. It will perform extremely well on your training data. But what if you were to use a completely different data set? Similar characteristics, but still different. What if you were to use a new set of points? You'll find that this curve performs pretty poorly. The training data is represented in green, the test data is represented in purple, and the curve that you fit through your training data is not a good representation of your test data. This is where you say that you have overfitted the curve to your training data. You'll have fantastic performance during training, but your actual performance in the real world will be bad. This is overfitting. Now, instead of this elaborate, complicated curve which passes through every point in the training data set, had you just represented the training data using a simple straight line, like we would in the case of linear regression, you might find that your model performs better. In summary, if your neural network has been overfitted, it means it shows low training error. The model does very well on training data, but has high test error. It works poorly with real data. There are many trade offs that a machine learning model has to make. Should it be overly complex versus simple? And this trade off is called the bias variance trade off. And if your model is overfitted, that means you've made a suboptimal choice in this bias variance trade off. An overfitted model basically means that your model has a very high variance error, but a low bias error. If you don't understand these terms, don't worry. That's what I'm going to explain just in a bit. We'll work with the same example where we try to connect dots. Now you can see that the dots can be connected in two ways at the very extreme. One, where you try to pass a curve through every point in the training data, and another where you make a lot of assumptions about the data and simply try to fit a straight line through the training data set. The model on the left, which we spoke of as an overfitted model, has a low bias error. That's because we have made no assumptions about the underlying data. We haven't made any assumptions for how it's distributed in space. We haven't assumed that it's a straight line or a simple curve. That has a low bias error. The model on the right has a high bias. A high bias because we basically assumed that a straight line is good enough to represent the underlying points in the training data. We've made more assumptions about the underlying data. Low bias, few assumptions about the underlying data. High bias, more assumptions. A model which has a low bias ends up being far too complex. That's because we try to mimic the underlying data and try to find patterns in the underlying data when patterns may not exist. The training data becomes all important in this very complex model. The actual other parameters of the model are less significant. At the other extreme, models which are high bias might end up being far too simple. The model parameter becomes all important then. The fact that we use a straight line to represent the data is far more important than the actual training data in the example that you see on screen. And really, if you want to have a complex model that works in the real world, you should make sure that you don't swing to either of these extremes. Models which are too complex or models that are too simple. Your bias shouldn't be very low nor very high. Let's move on and understand variance. The same model on the left, which we said had low bias, has a very high variance. Variance refers to how sensitive the model is to the training data. If the model changes significantly when the training data changes, the model is said to have high variance. So, if you imagine this curve which tries to fit every point within the training data set, if you move even a single point in the training data, this curve will change. So, the model on the left has high variance. The straight line that we've passed through the points, on the other hand, the model on the right has low variance. This is because the model is not dependent on the training data at all or hardly at all. The model doesn't change much when the training data changes. A high bias is equal to low variance. High variance models tend to be too complex. The model varies too much and is too sensitive to the underlying training data set. On the other hand, low variance models tend to be far too simple. They're not sensitive to the training data at all. Once again, if you're between either of these two extremes, that's when you get a good model. You don't want a model with too low or too high variance. Typically, if you're confronted with a model that is way too complex, that model is said to have a high variance error. This is typical of overfitted models. On the other hand, if the model is way too simple, we say that the model has a high bias error. It's your choice as the data scientist and the developer to choose the right model and tweak your parameters in such a way that you have exactly the right bias variance trade off for your problem statements. So, you should understand the characteristics of the various algorithms. Regression is a high bias algorithms. There are simple parameters. The underlying model is not very sensitive to the training data, it's less sensitive. On the other hand, machine learning models with very complex parameters and complex setups tend to be high variance. Decision trees are high variance, and dense neural networks are high variance models, which is why neural networks are prone to overfitting. So, when you're training your neural network, don't jump for joy if it performs extremely well on your training data. Test it out on your validation and test data before you make your final decision. A high bias model is one which depends far too much on the model parameters and too little on the training data. A high bias model is not very sensitive to the training data set and does not change much when the training data changes. High bias models tend to be overly simple. High variance models, on the other hand, are ultra sensitive to the training data set and do not make any underlying assumptions on the data. They don't have very strong model parameters. This means that high variance models tend to be overly complex. Overfitted models are high variance models.